Good morning. This will be the end of your 4-1 notes, and these are not mandatory, but I just wanted to finish out linear and angular speed and then go ahead and do a few conversions for you. So I asked you guys to do a try it for example 5. I want to go ahead and give the solutions for those. If I've got 0 degrees, I've also got 0 radians. If I've got pi over 6 radians, and I'm going to show my conversion, the way I do that to convert radians to degrees, I multiply times 180 over pi, and the pi's cancel, and 6 goes into 6 one time and goes into 180 30 times, so that's 30 degrees. 45 degrees, we're going to do our conversion factor in reverse. We're going to put pi over 180, and 45 goes into itself one time and into 180 4 times, so we get pi over 4. Pi over 3, I've kind of got that memorized from the unit circle, so that's going to be 60 degrees, but you would do your conversion factor the same way. You put 180 over pi, and then 180 over 3 is 60. 90, that's pi over 2, pi is 180, and 270 is 3 over 2 pi. Now, when we're looking at linear and angular speed, those are going to be kind of formula driven. So, and it's going to have to do with arc length. So, a central angle theta intercepts an arc of length s given by, and so the formula is theta equals s over r, where theta is in radians. Now, if the radius is 1, then s equals theta, and the radian measure of theta equals the arc length. So, if we consider a particle moving at a constant speed along a circular arc of radius r, so we have our radius, and we have our little particle, and it's going round and round. If s is the length of the arc traveled in time t, then the linear speed of the particle is s divided by t, which is the arc length over time. And remember, we have to measure arc length using probably our circumference formula. So if theta is the angle in radians corresponding to the arc length, then the angular speed is theta over t. So, like, there's your radius, here's your theta, here's your s, and your angular speed would be theta over however long it takes. So if it's moving slow, it would divide by a bigger number. If it's moving quickly, it would be dividing by a smaller number. So that's how we get speed. So, where is that applicable? If we look at our example 6, we've got a 6-inch diameter gear. So right away, I'm a visual person, I have to sketch it, but my 6 inches is the diameter, so automatically I'm gonna label my radius as 3. And it makes 2.5 revolutions per second. So that is given, and that is going to be the linear speed, revolutions per second. And so we want to find the angular speed of the gear, and so we are going to do that using our angular speed formula. Theta over t equals angular speed. So we want to think about what theta, or what angle, does it go through in what amount of time. So 2.5 revolutions, so that's 1, 2, and a half. So that's 2 pi, 2 pi, and 1 more pi. So it's going to go 5 pi's per second. So that is going to, and and our units for angular speed is radians per second. So that is the last example that I have for you. Let me go ahead and adjust my camera and show you all the calculations. And there you go.